All right, here we are. So we've got some problem sets. We were not completely done with the chapter 3 problem set, so we can finish that up today. We hadn't quite gotten to those last few problems. We had some geometric sequences, and then we also have a few word problems, just a few. And then when we're done with that, we can get back to chapter 6, which is, I think we just barely started it the other day. We may as well go back to the beginning, or at least the very close to the beginning. We started to talk about simplifying expressions, evaluating expressions, and I think we left off right about here with one of our first examples. So we'll carry on from there. And all right, so let's get back to this. All right, so we finished, all right, here we are. This is where we left off. So for each of the following geometric sequences, we're going to determine the first 5 terms, the 12th term, and the sum of those first 12 terms. Now, of course, like before, there's a couple of ways we can do this. We can write them out manually, or else we can use our formulas. Okay, so let's do both of them whenever feasible, just to see how they compare with each other. Now, the first 5 terms in this case, you can see that you have not been given the actual terms, but you do have the first term and the common ratio. So basically, you're starting with 12 and then doubling as you go along. Okay, and that's all this is. All right, so those are your first 5 terms. And then you need to ask or look for the 12th term. Now, you could certainly keep doubling them, but the numbers will get big, and I mean big, if you keep doing that manually. So this time, I think it might be a better idea to use the formula, which is AN equals A1 times R to the N minus 1 power. Okay, so in this case, we're looking for the 12th term, so we're looking at A12. The first term is 12, the common ratio is 2, and the exponent is 12 minus 1. All right, there we go. So it's 12 times 2 to the 11th. Oops. All right, well, 2 to the 11th is actually 2,048. Okay, so if you take out your calculator, you can solve these one at a time. 2 to the 11th is, in fact, 2048. And then when you multiply that by 12, you'll get 24,576. So you can see why, if we had doubled it ourselves, we could have done it, but man, look how big those numbers are getting. All right, and then finally, the sum of the first 12. So the formula for that one is a little bit messier than for the arithmetic sequences. So why don't we take a look at that? So I'll use my trusty equation editor here for this. All right, so here we go. Now, by the way, nobody expects you to memorize these formulas. So if you haven't memorized them, that's okay, because that's, even if we were doing this class in person, I used to give out a formula sheet, and these formulas were on it anyway. So you don't have to remember these, but you should recognize them when you see them. That you have to be able to tell them apart. And the way you can tell this one is meant for the geometric sequences is that it contains an R instead of an N. Okay, the common ratio rather than the common difference. Oops. Okay, so in the numerator, we have A1 times 1 minus R to the N. And then in the denominator, it's simply 1 minus R. Okay, so that means we'll have 12 times 1 minus 2 to the 12th power. And then we have 1 minus 2. Okay, so here we're going to have in the numerator 12 times, 1 minus 4096, all over -1. And when you do the multiplication, actually what you've got here is the ratio of 12 times -4095 all over -1. Of course, those cancel out. And by the time we're done, we end up with 49,140. All right, so that's how that one works. So you can see there were two negatives, but they cancel each other out. And so we end up with a total of 49,140. Very good. All right, now the next one is exactly the same, except for the numbers, of course, but it's the same procedure. So in other words, we'll start by writing out the first 5 terms: 8, 24, 72, 216, 648. All right, and how do we know that? Because what you're just doing is you are tripling it every time you go to the next term. You start with 8 and you triple it and keep tripling it until you get to 648. All right, now the 12th term, of course, will come from this formula. And so therefore, A12, the 12th term, is, so remember we started with 8, the common ratio is 3, and we're looking for the 12th term, so therefore n minus 1 is 12 minus 1. So we'll have 8 times 3 to the 11th. Now 3 to the 11th, as you can imagine, is a huge number. In fact, it's 177,147, and when you multiply that by 8, you end up with 1,417,176. Man. So you can imagine what the sum is going to look like. It's going to be enormous. So I'm going to borrow this equation and just edit it rather than starting all over again. So this time, the first term is 8, and the common ratio is 3. And so you've got 8 and 3 to the 12th is 531,441. Down here we'll have 1 minus 3. So this becomes minus 2. Okay. And then what we have to do is simplify this a little. Eight. Down here we have minus 2 again. And here we have minus 531,440. Okay. So when all of that is done, what we're going to have, and don't forget to divide out by that -2. Okay, 8 times -531,440 divided by -2 is 2,125,760. Yes, it is big, very big. Yes, it's OMG territory big. Yes, it's a whopper. Okay. Okay, but that's what happens typically with geometric sequences. They tend to get very big in a hurry. Unless they're negative or fractions, then they can get very small in a big hurry. All right, now, in the next batch, we're going to have not the A1 and the R given to us. Instead, we'll have the actual sequence. And so we should be able to easily figure out what A1 and R are going to be. And then from there, we can do the rest. Okay, so here, for example, the starting value A1 is 4, and the common ratio is 3 again. You can tell because each number is 3 times as large as the one before it. So in order to come up with the 12th term, we'll go back to this formula. And so A12 equals 4 times 3. And the exponent is 12 minus 1. So just by coincidence, we've already seen this one. 3 to the 11th. So we got, 4 times 3 to the 11th. And so 3 to the 11th is, once again, 177, 147. All right, so we multiply that by 4, and we wind up with 708,588. All right, and then we get the sum again, the first 12. All right, let's just borrow this one. All right, so what's different this time? We have A1 is 4. The common ratio is 3. And that's going to be raised to the 12th power. And in the denominator, we have 1 minus 3, because 3 is the common ratio. So we're going to have 4, 1 minus, so 3 to the 12th is 531,441 minus 2. So we actually have the ratio of minus 531,440 all over minus 2. Okay, and so finally, when all this is done, we end up with, wow, 1,062,880. All right, so we start up here. We have our 12th term and the sum of the first 12. Okay. Ooh, some of these are looking a little scary down here. Like this one, well, this one looks pretty normal. A1 is 6. The common ratio is 2. Okay, so in order to find the 12th term, we'll go back to our formula. All right, let's see, it's right here. And just plug in some numbers. A12 equals, so the first term is 6. The common ratio is 2. That will be raised to the 12 minus 1 power. So we'll have 6 times 2 to the 11th, which is 6 times 2048, and that equals
recording in
12,288. Beautiful. All right. And now all we have to do is the sum of the first 12. Let me just borrow this formula for a second. Okay, so for this formula, we need, on the numerator, we have A1, which is 6. 1 minus the common ratio of 2 raised to the 12th power. And then in the denominator, we have 1 minus r. 1 minus r. There we go. Okay, so what do we have here? 6 times 1 minus 2 to the 12th is 4096. All right, so we've got 6 times negative 4095 over negative 1. And when you multiply that out, you get negative 24,570. All right. Oh, wait, sorry, there's no negative there. My fault. The two negatives drop out. Let me get that out of there. There we go. So yeah, these two negatives cancel each other out. All right, so that one was nice and straightforward. Now the next two are a little bit trickier, as you could probably see when scrolling down there. So like for example, look at this one. All those ratios. What are we doing now? Well, in this case, the first one is clearly 1/2, and we can write it as 1/2. Let me do this one by hand because it'll be easier. Hold on a second. The common ratio, it turns out, is also 1/2. You can tell because if you take 1/2 times 1/2, you get a 4th. If you take a 4th times 1/2, you get an 1/8. And that's what's generating this geometric sequence. So when we put in our formula, let's see what we get. So to come up with A12, we have 1/2 times 1/2 raised to the 12 minus 1 power. So the way you can look at it is that these now are, this one implicitly has a 1 for an exponent. So you can just simply rewrite this as 1/2 to the 12th. And that in turn can be written as 1 to the 12th over 2 to the 12th. Now 1 to the 12th is clearly just 1. 2 to the 12th, as we saw earlier, is 4096. All right, so that's your final answer for that one. And then for the sum could be, because these are progressively smaller numbers, the sum could be a surprisingly small number. All right, so let's find out. So we started with 1/2. 1/2 times 1 minus 1/2 to the 12th power, which we've already seen right here, equals 1/2 1 minus 1 over 4096 over 1/2. Now you notice these halves cancel each other out. So here we have 1 minus 4096. Let's rewrite this as 4096 over 4096 minus 1 over 4096. And so we end up with a very interesting result, 4095 over 4096. It's just a hair under 1. All right, so wow, that was interesting. So yes, it's not surprising. All the other sums were enormous. This one is quite not enormous because, of course, we are adding progressively smaller numbers. All right, now I believe there's one more, and then we can do those word problems. Let's see, what do we have left here? Oh, there's two more. Okay, now this one, fractions again. Oh boy. Okay, well, that's right. We know what to do now. Okay, so for example, let's see what we're going to do here. A1 is 2/3. It turns out R is 1/3. How can you tell? Because the numerators are all two rather, but the denominators keep increasing by a multiple of 3. So in other words, if I started with 2/3 and multiply it by a third, I get 2/9. 2/9 times a third is 2/27, et cetera, et cetera, et cetera. So these are fine. Now, again, to get to the 12th term, we'll need this formula. Oh, okay, what happened there? Huh. All right, so let's do that. Two-thirds times 1/3 to the 12 minus 1 power. Okay, so we've got 2/3, 1 to the 11th over 3 to the 11th. And then we'll have 2/3 times 1 over. So 3 to the 11th, which we had a little while ago, was 177, 147 equals 2 times, and in the denominator, we have 531, 441. So you can see, yes, it's the same situation. The numbers keep getting smaller. The numerator doesn't change. It's the denominator that keeps increasing by a factor of 3. All right, so let's see what we can do with the sum. Okay, so let's plug in our numbers. So we started with 2/3. 1 minus 1/3 of the 12 over 1 minus 1/3. All right, so here we got a bit of a break because the numerator and the denominator cancel each other out, don't they? Yes, they do. Okay. We always like it when things simplify themselves for us, don't we? So we're going to wind up with 1 minus. Now, 1/3 to the 12th power is actually 1 over 3 to the 12th. Well, actually, it's this, but we can rewrite this as 1 over 3 to the 12th. And 3 to the 12th power is 531,441. Okay, so how do we do that? Well, let's rewrite the 1 as this ratio. Oh, what did I do? No, sorry. I just realized these are supposed to be 1s. Right, it would help if they match up with this number. That's better. All right, much better. So it's 531,440 over 531,441. Now we're all set. And again, it's a number that's just a hair under 1. And again, it's because we're adding a progressively smaller set of numbers. All right, so now what comes next? Oh, there's one more. This one has negatives. This is the first one that has negatives. So it's good practice. All right, so let's see what's going on here. A1 is -3. And then in order to alternate back and forth between negative and positive numbers, R has to be a negative number as well. Okay, so in other words, -3 times -5 is 15. 15 times -5 is -75, and so on and so on. So this is correct. So we'll start out by looking for the 12th term. Okay. All right, so let's do this one. So A12 -3, -5 to the 12 minus 1. Okay, -5 to the 11th. 48 mil. Oh, man. I'm going to run out of room. This one is so big. Minus 48 million. Um, 125. And we'll multiply that by -3. And we end up, wow, look at this number. I think this is the biggest number we've had today. 146,484,375. Man, that's a whopper there. But now it's going to get even bigger when we calculate the sum. Oh boy. All right, how big is big? Let's see. So we started at the beginning with -3. With -5 as our common ratio. All right, so don't forget about, be careful with those negatives. All right, so -5 to the 12th. Woo, 244 million. 140, 625 over 6. So -3. And then, let's see. This turns out to be minus 244, 140, 624. And then 122, 122, 070, 312. Ooh, all right. All right, so we've got 3 dreaded word problems here. Now, it turns out all of these are simply applications of sequences. These can be typically done in more than one way, I would point out. So let's see what we can do with these. So How about this first one? You have a car. Now, everybody knows, even if you don't own a car, you know that cars lose their value over time through a process called depreciation. And that's just the simple reality that the value goes down as you drive it more because you're basically wearing it out. So let's assume that for this particular car, the depreciation schedule looks like this. Now, this is pretty normal. Most of the depreciation does actually take place during the first few years. Now, there's a difference between the value of a new car and a 2-year-old car is much greater than the difference between, let's say, a 6-year-old car and an 8-year-old car. So the depreciation at the end of each year looks like this. The first year, now I'm going to treat these as negative numbers because this represents a loss in the value of the car. Okay, so negative 3,500. The next year it's negative 3,000. Then it's negative 2,500. And so suddenly you realize there's a pattern here. In fact, it looks just like an arithmetic sequence where A1 is negative 3,500. And in this case, the difference rather is positive 500, because if you take, let's say, the negative 3,500 plus 500 equals minus 3,000. And then if you take the negative 3,000 and add 500, it becomes negative 2,500. So if you treat A1 as a negative number, then the common difference is positive. So the question here is that how much value does it lose in the 7th year? And that simply means what is the 7th term in the sequence? So you can interpret that to mean we want to calculate A7. Now remember, this is an arithmetic sequence. So we're going to use that special formula for the arithmetic sequence, which is AN equals A1 plus n minus 1 times d. Now, in a case like this, you may feel free to write them all out too, because it's really not that complicated a sequence. And in fact, maybe we'll do that right now, just real fast. Oops. 1, 2, 3, 4, 5, 6, 7. Yes, so term 7 is the negative 500, but let's use our formula. Okay, so A7 would therefore be minus 3,500 plus 7 minus 1 times 500 minus 3,500 plus 6 times 500 minus 3,500 plus 3,000. And there you go, minus 500. So in year 7, it only loses $500 because the car isn't worth very much anymore. And so the depreciation declines every year. That was part A. Now part B says, how much will the car be worth at the end of the 7th year? So this one is a little bit tricky. We haven't done this before. That's why I'm saying that. So here's what you have to do. This equals the purchase price of $27,000 minus the total depreciation during the first 7 years. And so in other words, what you're being asked to do is this. 27,000 minus S7. That's your answer right there. So you're being indirectly asked to calculate the sum of the first 7 terms. Now, again, you could probably do this yourself just by adding them up manually, but let's use the formula. All right, hold on. Let me use my trusty equation editor here to get this going. So S7, well, let's just say that Sn in general, let's see, Sn is the ratio of, hold on one second, n times A1 plus AN whoops, AN all divided by 2. Okay, so we're going to have, in this case, 7 for 7 years, negative 3,500 plus negative 500, because that's A7, all divided by 2. So we're going to have 7 times negative 4,000 over 2, and that turns out to be minus 14,000. All right, so S7 is actually 14,000, negative 14,000. Oh, you know what that means? I just realized, because we're treating the depreciation as negative, I'm actually going to add this to my 27,000. Okay, so it's 27,000 minus 14,000. So the car, after 7 years, is still worth $13,000. All right, that's the bottom line. Okay, so if you add up all the depreciations one at a time, you'll end up with the same result. Now, in reality, it doesn't work out quite so nicely, but there are formulas that you could use. They're just much more complicated than this. But let's just say that this is how it works, that you can very easily calculate the value of your car by knowing how to add up the numbers in an arithmetic sequence. So that, I thought, was kind of a fun application, because some of you probably do have a car and you know perfectly well that the car loses value every year, especially when it's new. All right, like I said, that's when most of the depreciation takes place, but later on it starts to decline, but it still goes down every year. All right, now look at this application. At some university that we don't name here, the first parking violation in the faculty lot results in a fine of $5. The second time you have to pay $8. The third time is 11. So if you write out the pattern of tickets, you see that there's a pattern here. Oh my God, yes. So it's almost like an arithmetic sequence, starting with 5 and with a common difference of 3. So now this one student has convinced her parents to pay her fines, but they've told her that if the fines reach $100, the car will be sold on eBay. Now, this unfortunate student has received 8 tickets. So the question is whether or not she's going to get to keep the car. So basically what it's saying is, what is the sum of the first 8 fines, or the first 8 terms in the sequence? All right, so that means before we do anything else, because this formula requires us to know AN, we have to first figure out the 8th fine. All right, let me just tidy this up a little. So we can't just plug what we have directly into the formula, because we don't have this AN term. So we need A7, or 8 rather. She has 8 tickets. So there's a couple of options we have here. We can continue writing these out just to check. So there'll be 5, 8, 11, 14, 17, 20, 23, 26, 1, 2, 3, 4, 5, 6. Okay, so those are the first 8 fines. Now A8 can be found as well with this formula. Okay. So therefore, A8 must be 5 plus 8 minus 1 times 3. 5 plus 7 times 3. 5 plus 21. Yes, 26. But the question here is, what's the sum? All right, so here's our sum formula down here. Okay, so now we can plug in our numbers. Okay, now it doesn't look promising though, does it? The sum has to stay below 100 before the student gets to keep her car. All right, so we have 8, 5 is the first term, 26 is the second, and 2, so we're almost there. 8 times 31 over 2 is 124. Ooh. You know what that means? Yes, you do know what that means. No more car. I know. Well, I hope she doesn't live in Brooklyn. That would be some walk. So yeah, no, the parents are upset. She keeps doing this, and they're like, "Oh no, we're going to take that car away from you." And I guess it's going to happen. So she'll not be able to keep the car. Who knows? Maybe she gets all A's. They'll let her have it back. All right, now this last one is a little bit more challenging. I'm just going to tell you how this works. This one will not appear on your test, by the way, because it's a little bit more advanced, shall we say. But we start out with $500 in our checking account or savings account. And what happens is every year you earn 5% interest, let's say. And so we're going to keep the money there for 10 years. So after 1 year, we have 500 times 1.05. And this is the part that you wouldn't have known about. So that's why I'm not going to put this on the test. In other words, what this is telling me is that after a year, I still have my original $500 plus another 5%. Then after 2 years, but I just want to point out that we are going to eventually get to this topic in chapter 8, but we haven't seen it just yet. So we're not going to have this on our test. So now, after 2 years, if you leave the money there, which is what we're assuming, you'll have $551.25. And then this keeps going, and we do the same thing every year. Okay, so we actually have, and it keeps going, so you actually have a sequence that looks like this. Now, because each year the sum is being multiplied by the previous year's balance and 1.05, we could think of this as a geometric sequence where A1 is the first year's balance of 525, and R is 1.05, which implies at the end of 10 years, now this is the other tricky part. The balance will be not S10, but A10. Okay, because that's how much you'll actually have. Not the total, because they're not actually adding them up as we go along. It grows, but you're not collecting 525 plus 551, et cetera, et cetera. You're just getting what's left at the end of 10 years. So because it's a geometric sequence, and because the common ratio is 1.05, we're going to have this formula, AN equals A1 plus No, sorry, wrong one. R to the n minus 1 power. Okay. All right. So that means that A10, which is what we're aiming for, is 525 times 1.05 to the 9th power. And that adds up to 814. It's approximately 8.14447. I think that there's more digits than that. Let me just double check that real fast. 105 to the 9th. Yeah. It's a lot. Yeah, it's like 4473134. Now, because this is dollars and cents, though, the bank will round it to 814.45. If you notice, because you've got 447 here, so they'll round it up to 814.45, and that will be the amount that's sitting in your account. And now, of course, you can do whatever you want with it. So you start out with 500, and after 10 years, you have 814.45. So yeah, you can see this one is a lot messier than what we've been doing. So while it's fun to see this, this will not appear on your test. Beautiful. All right. Well, you know what? These are done now. At long last. Well, this one seemed to go on forever, didn't it? Yes. So we're ready to get back to chapter 6. Very exciting little chapter. And so let's see what's going on there. Okay. All right, I have it right here somewhere. Here it is. Now, we'd started to look at evaluating expressions, and I think we stopped right here with this example. So imagine you are going to a Starbucks. Imagine that it's actually open, and or is it? I don't know. Is that Starbucks open over by Fort Awesome? No. Okay. All right. That's how you know things are not normal when the Starbucks is closed. That's a pretty sad sign. Oh, that one is. Yeah, just not the one in the school. Okay. Yeah, the rest of them are open. Now, suppose that the latte, the actual cost is $2.89, but the sales tax is 6%. So, normally they just figure out for you, and you hand them the money and you walk out the door and you don't think about it. But how did they figure out the actual sales tax? Well, there's a few ways we can do this, but we can think of it this way. We've got the original 289 plus 6% of the price, 6% of 289, which you could do that separately if you want to. In fact, if you do, you're going to get 289. Let's do that two different ways. 6% of 289 is about, see, we're going to have some rounding here. But you can see if you combine those, you're going to get 3.0634, which they would round to 30.06. But if instead what you can do is consolidate algebraically these two, so there's an implied 1 here. So you can actually rewrite this as 2.89 times 1.06, and you'll end up with this 306 anyway. And there's still rounding going on, but you'll end up with the exact same number. So you can do it one of two ways. You can either figure out separately the sales tax and add it on, or you can just consolidate them into one expression. 2.89 times 1.06 will also give you the right number. Okay, because again, it's like you're factoring out 289, and again, with the understanding that there's an implied 1 here, right there. All right, so that was pretty straightforward. And so if you ever wondered, how are they figuring this number out? Well, that's what they're doing. There's some sales tax that applies where you live, and they multiply that by the price, and that's what you end up with. Now, if you've ever visited foreign countries, especially in Europe, they have a tendency to include that in the price. So in other words, if you're in England and you walk into a Starbucks and they say that the price is £3, that means including the tax. And so you hand them £3 and you walk out the door. It's already built into the price. Here it's written out separately. So the two countries do things differently, obviously, but most of Western Europe, the tax is already built into the price. But having said that, usually the tax is much higher in some of those countries, and even in Canada, the sales tax can be well into the double digits, like 16, 18. One year I was in Quebec City, and the sales tax was 21%. I couldn't believe it, 21%. Oh my God. So we should not complain in the United States about, at least not our sales taxes. All right, anyway, now how about this one though? Here's a department store that's offering a 20% discount for all furniture during the month of January. So suppose you say to yourself, you know what, that couch we have in our room is all beat up. We need a new one. Let's go buy one. It's on sale. How much will we actually have to pay for it after taking into account the discount? All right, so now we can write it like this. We got the $600. Now we're subtracting the 20% discount. So you could either write it out as 600 minus 120, or you could consolidate these two. This would be one. Let me just write this in here again. So what you're actually doing is you're rearranging it as 600 times 1 minus 0.20, or 600 times 80%. So now they're asking you for $480 instead of 600. Now, of course, there'll still be sales tax, but the actual retail price now is now been reduced to $480. So if you have enough roommates, you can afford that. Okay, especially because that's why I got beat up in the first place, because there's always so many people on it. All right, so it works that way. You see that, how that works? The more roommates you have, the more beat up your couch gets, but then the easier it is to pay for a new one. Okay, well, I guess now you're probably at home anyway, but still, if it's on sale, you might want to think about getting one. Now, linear equations. Now, this is something you're probably all very familiar with, but we need some practice. We're going to solve for linear equations, which means we have a straight line and we're essentially looking for the point where it crosses the horizontal axis. All right, so for example, let me show you a quick picture of that. Let's say that, for example, our equation is y equals 2x plus 4. Now you can see it crosses the horizontal axis here, but where is here? How do we know what that point is? Well, here's what we can do. Set this equal to 0. Because the logic being that this is where the horizontal axis is where y equals 0. So by doing that, we can identify this is the point -2, 0. So we say that it crosses the axis, the x-axis at -2, 0. And so the idea here, though, is that -2 is the solution of y equals 2x plus 4, because this is the value of x at which y equals 0. All right. By the way, sometimes the word solution is replaced with root. You may have heard that word before, the root. All right, let's look at some simple examples. Now, a lot of this is just basic algebraic manipulation, but you know what? We could probably use some practice. Okay, so for example, let's try this one. How would we solve this one? Remember, the idea is this. You want to isolate x on one side of the equation. This is the basic strategy. And the constants on the other side of the equation. That's what you're essentially trying to do. Now, there's always a lot of ways of doing this. But usually there's one that might be a little simpler. It's up to you. Whatever just do whatever you have to do to get x by itself on one side and all the constants on the other side, and do it in a way that's as straightforward as possible. Otherwise, you'll end up making mistakes. So like here, for example, it's pretty clear that you want to get the 7 over here to start with, just as a starting point. And how do you get it over there? You want to subtract it from both sides so that it drops out from the left-hand side. So let's see how that works. So you subtract the 7, and so these drop out, and you're left with 5x equals 8. Now, we don't want to know the value of 5x. We want the value of x. So the only way to do that is to divide out both sides by this 5, so that when you're done, you have x equals 8/5, and you're done. Now, how do you double check this? You go back to the original equation and see what happens if you replace that x with 8/5. Oh, what do you know? These cancel. 8 plus 7 is 15. 15 equals 15. And that means we've successfully proven that our answer is correct. Okay. All right, now let's try another one. Ooh, this one's a little trickier. First, of course, get this 9 over to the right-hand side by subtracting. Now here we have a -3, so we can just simply divide both sides by that -3. But then don't forget, this ratio of 33 to -3 is not 11, it's -11. All right, so again, we can simply confirm this by going back here. And let's plug in -3, -11 rather. And that proves that we've done this correctly. Very good. Congratulations. All right, so you've done this many times before, but it's just that sometimes some of these are more challenging than others. But still, ultimately, your job is to get all the x's on one side, the constants on the other, and then when you're done, you'll have x equals some value or other. All right, let's look at this one. Now, this one's even messier because we have to apply the distributive property before we do anything else. So we'll have 3x minus 3 times 2. The rest stay the same. And now I've got 3x minus 6 plus 4. When you have more than one term, well, these are referred to, I may have mentioned this before, as like terms. That means constants or x's or x squares or whatever. You should always deal with those first. Okay, so in other words, this is equal to 3x minus 2. Okay, now it's easy to see. Here we can actually do a couple of things. why don't we just keep the x's on the left-hand side and move all the constants to the right? So let's jump ahead to the next slide where we're going to do exactly that. Okay, now let's add 2 to both sides to get rid of this one. 3 equals 2x minus 3. Now this has to get moved over here by subtracting it. Okay. And that's our final result. So heading back to the original equation, we can prove this. Although in a bit of a roundabout way, we're going to have 3 negative 5 plus 4 equals negative 6 minus 5. We'll move that down here. Minus 20 plus 4 equals minus 11. Nope, sorry, minus 15, my fault. Minus 15 plus 4, that's right. And then finally, minus 11 equals minus 11. Perfect. Now, the next one is pretty nightmarish, but I think we're ready for it. I think we're all warmed up by now. You know, it's like when you first get up on any morning this early, you're like, oh, okay, math, I don't know. But now you're all warmed up, all right? And so now you're ready for a challenge. So what I'm going to do is write down this equation. I don't want you to see the answers, though. I want to make sure we can all do this. It's a little messier. So let's try this one. I want you to try this one. All right, hold on. It might, I'll give you like 2 minutes, maybe 3. And you'll see there's going to be a bit of messy algebra. And oh my God, fractions. All right, so why don't you take a couple of minutes and solve for x? All right, let's do it. Okay. 2 minutes, 3 minutes. Okay. By the way, helpful hint, it's a very messy answer. It's not 3 or 7, believe me. It's something pretty messy. By the way, here's a helpful hint. Why don't you start, if you're stuck, why don't you change this thing into ninths? That might help. Okay, so in other words, 5/3 times 3/3 is 15 ninths. All right, and that'll make it a little bit easier. All right, so now of course you're all probably approaching it slightly differently. So I'm going to add 15/9 to both sides. And then if I'm going to do that, I'll have to subtract 9x from both sides. Now I'm going to have to divide both sides by -7. So let's see if I have any room here. So x actually equals 19/9 over -7. Now, algebraically, this is equivalent to 19 over 9 times 1 over -7. So my final answer, and I did say it was going to be messy, is -19 over 63. Oh my God. Oh, that was brutal. But like I said, it's 9:30. You're all pumped up. It's like you were going to go out and run 10 miles, and you've been loosening up all this time. All right, well, here we go. Okay, so let's see what's next. Ooh, look at this one, an application that you're probably familiar with. Suppose that in a math class, the final grade equals the average of the first 3 test scores. A student has already received grades of 80 and 90 on the first 2 exams and needs an 86 to get a B+. What is the minimum score he can receive on that 3rd exam to get that B+? All right, now this one's a little trickier. Why don't you try it for a couple of minutes? Maybe you'll get to it, maybe you won't. If not, we'll go through it all together. But I just want to see how far you can take this one. All right, so give that one a shot. And you've probably done this yourselves, by the way. All right, I'll give you 1 more minute. All right, so here's one way to approach it. First of all, the average of the tests, these T's, by the way, represent the scores in the first 3 tests. All right, so we've already been told that this person got an 80 on the first test and a 90 on the second. The sum of the 3 over 3 is the average. And we're aiming for an 86. So you can rewrite this now by plugging in the numbers. And all that's missing is T3, which means this is what we need to solve for. So because the right-hand side is being divided by 3, we can basically get rid of that by multiplying both sides by 3, and we end up with 86 times 3 equals just whatever's in these parentheses. So 3 times 86 is 258. Now we can drop the parentheses, and then we're going to wind up with 258. I'll just pencil it in here. Is 170 plus T3. And now look how easy this is. All you have to do is subtract 170 from both sides. And so here it is again. There's your 88. So in other words, 80 plus 90 plus 88 over 3 is 258 over 3, which is exactly 86. So if the student gets an 88 or better, that locks up a B plus. I'm sure you've done this yourselves. You go into your final exam and you say, listen, what grade do I need to get a certain letter? And that way you have a target in mind. I don't know. I found that it was helpful when I was a student to have that number in mind so you can, just get a rough sense of how well you're likely to do. Now, here's an interesting one. It's a little bit more abstract. Suppose that multiplying a number which we'll call x by 8 and then adding 3 results in a value of 27. So whatever this mystery number is, we want to solve for it. So go ahead, give it a shot. I'll give you a minute or two, and let's see if we can come up with this number. Now, this one should be easy because there's no averages involved, and it's a nice number, okay? It's not negative 1963rds or whatever. All right, take a minute and just see if you can come up with that one. The question, of course, is how to set it up. That's, of course, the big challenge. All right, so how would this work? Now remember, you're being told that if you multiply this number by 8 and then add 3, you're getting 27. So this is your starting point. Once you get this straightened out, the rest is easy. You just subtract the 3 from both sides and divide out the 8. Oh my God, it was so easy. So does this work? Multiply 3 by 8 and then add 3. Does that give me 27? Why, yes, it does. Oops. Of course it does. All right, very nice. All right, what else do we have here? Inequalities. Now, you might recall that in addition to equalities, we also may encounter inequalities. So let's just quickly review here. This symbol means less than, and that also sometimes pronounced strictly less than. This one, of course, means less than or equal to This one means greater than. Or sometimes strictly greater than. And then finally, this one is greater than or equal to. Okay, so that little extra bar there implies that it's also possible for it to be equal to. So, all right, so less than or strictly less than or equal to, because that little bar is here. This one is greater than or strictly greater than. And then finally, we have greater than or equal to. So those, obviously, we have to be careful with these because it matters a great deal which one we're looking at. So let me just show you quickly some examples. So for example, if I told you that, suppose that there was a class and you have to be less than, you can only join the class if you are less than 21. For some reason, who knows why they would do this, but this means 21 doesn't count, does it? That's not good enough. You have to be less than 21. Okay. Or if I tell you that X is less than 7, that means that X cannot equal 7. But here, X can be less than 7 or 7. In other words, it can be 7. If I say X is strictly greater than 7, X cannot be 7 here either. But if I say this, I say that X is greater than 7 or equal to 7. Okay, now also I want to show you some interesting terminology here while we're talking about this. Let's try these. If X is strictly less than 0, that means that X, by the way, I don't think I ever showed this to you either. Hold on one second. If I write an arrow like that, this is important. Now, this is not the proper arrow symbol. In fact, I could probably look it up if we, hold on one second. Oh, do we have that here? No, I can find it. Let's see if I can reproduce this. No, it doesn't work in PowerPoint. It only works in Word. Hold on. This is kind of awkward. There we go. There's my arrow. All right, we're going to use this. This arrow is in English, you would say the words implies. Okay, so that symbol means it replaces the English words implies or implies that. It can come in very handy. So this implies that X is negative. Oops. X is negative. Now, why am I saying that? Because What else could there be? Hold on. If X could be either, now there actually, yeah, you know what? There's a symbol for this too. I don't think I have it right here. All right, well, that's not a problem. We'll go to the internet. The problem with these symbol boxes is that it can take forever to find them. Luckily, they all have a code attached to them that I can use to find them. Okay, 2264. And there we go. All right. So this symbol, less than or equal to, means, oh boy. Here we go. So let's use our special arrow here. Man, why are they so tiny? All right, let's try that. This is so frustrating. No, what is it doing? All right. You see, this is why we just write this stuff out in English sometimes, because yeah, the technology is still a little awkward here. All right, whatever you say. This implies that X is non-positive. Okay, so in other words, because we allow for the possibility of it being zero, we're going to say that it's no longer strictly negative, but, oh, for God's sake, hold on. Non-positive. All right, that's it. Man, that was a pain, getting all that done. I don't know why they make it so hard. But there it is at long last. I should have done this in advance, but I didn't think about it. Man, what a pain this is. All right. So now maybe it will allow us to do the reverse. So there's two other possibilities for us to consider. If X is strictly greater than zero, then we say that X is positive. But if it's greater than or equal to, let's now need that symbol. Hold on one second. Oh man, I'm not sure if this was worth all the trouble, but let's carry on with this. Uh, 2265. All right. And of course, it's extremely tiny. All right, that means that we call it non-negative. All right, I hope you see what I'm doing here. This is just terminology, but still, you have to be comfortable with these terms. So if X is always less than zero, not including zero, we say that it's negative. But if we allow for the possibility of zero, it becomes non-positive. Okay. On the other side, if it's strictly greater than zero, we call it positive. But if it's possible to be zero or positive, we call it non-negative. And again, the arrow is mathematical shorthand for implies, or implies that. All right. So why did I mention that? Because again, we have to be very careful with these four symbols. They do not mean the same thing. Okay. So when you hear those terms, you know what it means. All right, here we go. Well, now here's what's different about solving for inequalities. Let me just show you a graph real fast. This is what we're building up to. We're not trying to introduce a new concept here, but what we are trying to do is explain how to solve for an inequality. And there's a couple of important differences here that I want to remind you of. First of all, when we have an equality, as we saw earlier, remember before we said y equals 2x plus 4. Oh, that's not a good graph. Hold on. When we did this earlier, y equals 2x plus 4, we discovered that the solution is this one point, and the solution is 2. With an inequality, it's a different matter, because look what happens. Suppose that my function is something like this. Y is less than or equal to 7. That would include all of these values, everything. So when you have something like this with an inequality, there are an infinite number of solutions. With an equality, there's one solution only. And that's a big deal. We'll see that when we get to this, but so this is what we're building up to. We're going to solve for inequalities. Like, here's a good one. How about this one? That represents this line, x equals 7, and everything to the left of it. Anything, so x could be 6, 5, negative 100. It's a set that contains every value up to 7. So in fact, you could write it like this. Minus infinity, or actually not like that. You could write it as an interval from negative infinity up to and including 7. These are the solutions. And you can see it's an infinite set. That means it covers everything to the left of x equals 7. Now that's going to have an influence on the way we solve it. Okay, so, but I tell you what, since it's 10 o'clock, we'll probably have to start right here. So what I'll do is I'll post the solutions to the third problem set that we just finished, and you can study them as you wish, when you get a chance. And then I think what we'll do here, since chapter 6 still has quite a long ways to go, what we'll just do is next week, at least on Monday, we'll just finish up or get as much of this chapter done as we can. Now, having said all of that, the first midterm is based on chapters 5 and 6. So not that we're going to have a midterm anytime soon, but we're getting closer. All right, a little closer. The light is at the end of the tunnel. It's coming, just not yet. But when we're done with chapter 6, then we'll have to continue reviewing. And at some point when we're done, then we can go ahead and have our first midterm. But for right now, just go back, review the problems that we finished earlier today, make sure you understand them, and then follow along and read the slides and make sure you understand what we've done here. And you'll be good. All right. So I'll see you all on Monday.
Thank you.
Thank you.
Okay, you're welcome.
Thank you.
Okay. All right. Bye.
Thank you.
Okay. See you later.